chapter that we studied. So let's start with the protein structure and function question page. These are the question pages I sent you by email. I really hope you try them yourself before this class, before now, because it's really much more efficient this way. Okay, so let's start with one. The interactions that stabilize the alpha helix in a protein should be stated. So what are the interactions there? Hydrogen bonds between several parallel alpha helices. What do you think? Is that correct?
B.
Sorry?
B.
Right, so let's go straight to B. Okay, so hydrogen bonds between chemical groups in the protein backbone. So if you recall, these are the interactions that stabilize the structure, and not hydrogen bonds between several parallel alpha helices, because it's an internal thing inside each helix. Let's see why C and D are also incorrect. Hydrogen bonds between the protein residual groups. So this is, okay, so it's not between the residual groups. Remember, the residual groups is the alternating part of each amino acid. Hydrogen bond between several perpendicular alpha. Again, it's not between alpha helices. Never mind if they're perpendicular or not. Okay, so answer is B. Number 2. Every dihedral angle in the polypeptide backbone has a certain range of possible values. So we haven't really stated this fact as it is written right here, but the Ramachandran plot sort of shows us exactly this phenomenon. Okay, so which sentence is correct? There's a relatively large range in the proximity of a large amino acid. Large range of possible dihedral angles. That's the idea. So what do you think? Does this make sense? Okay, so again, it's a question of I don't know that you have to deduce for something we've discussed. So we've discussed the tiny glycine amino acid and the proline amino acids and the way they would look at on the Ramachandran plot, and I think you should remember these two examples while answering this question. So if any, there will be a relatively small range of possible dihedral angles around a large amino acid, an amino acid with a large residual group. And indeed, that's what we see on average, generally speaking, in the Ramachandran plot. There is a relatively large range in the proximity of a small amino acid, so B is just the opposite, it's correct. It's exactly what the particular specific example of B we saw for glycine. C, the range is unaffected by the nature of proximal amino acids. Incorrect. D disproved C anyway. So D, the range is small for short polypeptide. The length of the polypeptide does not play any role in calculating the degrees around each dihedral angle, right? So, and this is what the question is all about. The range is large for a long polypeptide, same thing as D, so the only correct here is B. Only correct answer. Okay, in proteins, structural motifs exist. Mark the incorrect sentence. So who says that? What about A? Is it correct or incorrect? Motifs are different combinations of secondary structures. Correct. So it's not. So it's not what we're looking for. B. A motif implies the protein function. Correct. It's a fact we stated. C. A motif will include the exact same sequence in different proteins. So we discussed what do we mean by saying a consensus sequence, and then a consensus sequence either in the nucleotide level or at the amino acid level. It's a similar sequence and not identical. Usually it wouldn't be identical, so C is incorrect. Let us make sure we understand D as well. D, a protein can have more than one motif. Yes, the answer is yes. Okay. For instance, if it's an RNA binding protein, so it will have an RNA binding motif on one region of it, and another region, I don't know, would interact with another protein, so it has another motif to function there, and or something else. Okay, number 4. In homologous proteins, there is. Okay, so homologous here in the evolutionary sense. We've discussed it quite briefly, only one slide, but still we've maybe softly, but we have defined what homologous proteins are. Okay, an identical sequence of amino acids. Actually, it's the same concept as the consensus sequence. So it's not identical. B, a similar sequence of amino acids compared to an unhomologous protein. That's correct. An identity in the secondary level. So again, no identity, just similarity. A similarity in the secondary level compared to an unhomologous protein. So B and D are correct, hence H. Okay, some of the question is with the other page. Okay, so number 5. Chaperones are involved in proper folding of proteins. Remember, chaperones and molecular chaperones and chaperonins, these are the two different kinds of chaperones. Mark the correct sentence for most proteins in the cell. So A, chaperones fold proteins to a thermodynamically unstable shape. Right, it's incorrect. They only support the proper folding towards some stable point. Can be a local minima. It doesn't have to be a global minimum. Chaperones fold, so this is incorrect. B, chaperones fold proteins into a shape to which the protein is unable to acquire spontaneously. Incorrect. They're only promoting, make the whole process more efficient, more rapidly, but proteins can attain their proper folding and usually do attain the proper folding. Sorry. C, chaperones promote proper folding. Correct. C. And D, chaperones slow down proper folding. Incorrect. So just C. Number 6. An enzyme active site includes. It's a plain terminology question, just definitions. So who wants to? What's the right answer? Ligand site, right? Then a catalytic site. So A and D, right here. Yes. Okay, hydrophobic site. The protein, an enzyme might have an hydrophobic site, but per definition, it wouldn't be part of the active site, and the same for B and C. Okay, here it says. Okay, 7. Passing of a protein mixture through a column. The group of methods we call chromatography is a technique for protein separation. What are the features that allow separation in this technique? So you remember that there are several techniques, each one of chromatography, each one separate proteins by different features. And among the different features we mentioned, which would you find here? Which do you find here? So charge is true and size is true. What about C, place in the cell? Not really. Involvement in molecular pathway, again, not really. I mean, a protein can this or that charge or size and be involved in this or that processes. So it's A and B, G. All right. Okay, so that's it for protein structure and function. Now just two tiny questions. I think one of them you shouldn't be really able to answer because of the microRNAs. For the molecular genetic mechanisms, tiny chapter. Okay, so number 1, below are several kinds of molecules. All of them are RNA molecules. Match to each one the role or roles it performs in the cell using the following list. So you have a list of functions, roles, decoding of a nucleotide sequence, part of the ribosome, regulation on gene expression, part of the spliceosome, in information storage. So you should come back to this question in a couple of chapters because we haven't mentioned yet snRNA, microRNA, and siRNA. So maybe we'll just skip this one for now. We'll come back to it later. Okay, this is just one question. In the DNA molecule, so what's the correct sentence or sentences? A, the strand orientation is anti-parallel, right? Essential part of the DNA double helix. B, the strand orientation is parallel, incorrect. C, covalent bonds hold the two strands together. What do you think? Between right, it's only hydrogen bonds, what we call Watson-Crick bonds. Covalent bonds exist between each building block of each chain. So C is incorrect. Hydrogen bonds hold the two strands together. This is correct. A and B. Okay. All right. where we stopped last time. I'll give a short recall of where we stand in the chapter. We'll just give you 1 minute. I saw that Camille came, so, and he has a laser. One second. So we are in the chapter of biomembranes and cell architecture, having these sections in it. We went through the basic structure and characteristics of biomembranes, a bit about lipid compositions and the way they dictate the morphology of the plasma membrane. And then we were just about the middle of the second section, the organelles of the eukaryotic cell. We discussed each of these organelles separately, just briefly, but each one separately, so schematically how it looks in the cell, and just mention each organelle. And now, along the way, you probably noticed that we've mentioned a couple of organelles that end with a zone. So let's make an order in all the different zones. Okay, so these are all vesicles. That's their common feature. Phagosomes are vesicles that internalize pathogenic microorganisms from the cell exterior. So they internalize the biggest substance that a cell can take in from the surrounding, right? Because it's microorganisms. All right. Second kind of vesicles that we mentioned are endosomes, and they take up smaller molecules into the cell, which are macromolecules. So the process of the phagosomes are involved in is called phagocytosis, and here we have endocytosis. And we actually also have picocytosis, which is not mentioned here. And picocytosis internalizes smallest substances from the cell exterior, and it starts to play a role in probing of the environment by the cell. These processes have different components and different mechanisms of action, but still they're quite the same, have a lot in common, and they just internalize big substances, smaller substances, and we've also mentioned picocytosis. And after substances are internalized by either of these two processes, they are merged into a lysosome, which are acidic organelles, acidic vesicles that exist in the cell cytosol. And these organelles have in them a battery of degradative enzymes. These are enzymes that degrade, destroy different substances. And there's also in the cell a process in which an aged organelle is degraded, and that's called autophagy, which means just eating oneself. Now recall that this is true for transmembrane proteins. Remember, these are proteins that interact with the membrane just by being embedded in them and having two ends sticking from either side. So for these proteins and for proteins that are internalized from the outside, autophagy, and for aged organelles is the process by which these components are being degraded. And just recall that for cytosolic proteins, and actually also nucleic proteins, they are degraded not by the autophagy process, but in proteasomes, which is the endpoint of the ubiquitination process, which was discussed. Okay, now inside lysosomes, we've mentioned there's a battery of different degradative enzymes, and here are three examples of such enzymes. They are all named after the substance that they degrade, and then they have a A in the end that denotes the fact that they destroy or hydrolyze different components. So nucleases are enzymes that degrade substances that are made of nucleotides, RNA and DNA. All of them you'll find in lysosomes. Proteases degrade proteins and peptides, okay? And phosphatases remove phosphate groups and necessary initial steps in degradation of many proteins. And let's put these three components we've mentioned, different zones, in a spatial context in the cell. So phagosomes, endosomes, internalized substance from the smaller substances from the outside, and the process of eating oneself are all converge in what we call a secondary lysosome or a mature lysosome, where the substance is actually being degraded. Okay. Now, to try to get an intuition of how the things look in the tissue, so to speak, we'll now play a game of looking at electron microscopy figures to try to wisely guess on which organelle we're looking at. And just before that, a word of reservation. Okay, so different cells have very different morphology from the outside and also from the inside. Some cells have gigantic ERs, endoplasmic reticulum, and Golgi. These are usually cells that have to do with secrete a lot of proteins, like cells that are located in the intestine. Another extreme example is the sperm cell, which is really just a very dense chromatin and a lot of mitochondria in the region where the tail of the cell protrudes, what is called the flagellum, to produce a lot of energy and to enable very rapid movement of the cell. Because all it has to do is to take the DNA information from one place to another. So cells look very different from one another, extremely different, but still, let's try to look at cells. We won't mention it on which cell we're looking at, and just try to guess on which organelle is there. So, what do you think is this? Okay, another word before we play it again. So, electron microscopy, just very briefly how it works. We take a tissue, we slice it very thinly, we cover it with metal, then we shoot a laser beam and read the scatter that's formed. And we can then transform it to an image. So just one sentence, or you can read it more about electron microscopy. So things look different from how they're really there in the tissue. So anyone? What's this? Sorry? Mitochondria, right. So you see the foldings. The inner matrix of the mitochondria is folded on itself. That was a black screen. Okay. Okay, mitochondria. We'll see another example of mitochondria later. So what's this? Right, so that's nucleus. I'm not sure what the arrow tries to say. Maybe it's the chromatin, either the chromatin or the nucleus. So it's the nucleus. What about this point, specifically this point right here? Okay, maybe they tried to point at a pore. I'm not sure. Okay, so there are pores in the nucleus. Sorry, in the nuclear membrane. If I remember correctly, so you see here two layers. Two thin black lines, and as you remember, the nucleus, in opposed to other organelles in the cell, has two membranes that surround it, so nuclear membrane. But remember, you're correct, there is also pores there. But this is secretory vesicles. They are extremely dark, and they are always like this in electron microscopy because they are very densely packed with substances, neurotransmitters, for instance. Yeah, sometimes empty vesicles, but these are secretory vesicles. Usually, from my experience, they are darker than the rest of the cell. Okay, what are we looking at here? Sorry? Ribosomes. I'm not sure. I don't think so.
Smooth young?
I would say the smooth young. usually in cells, not always, but usually the Golgi is farther towards the plasma membrane than the ER. But I think in this cell, got it the other way around. Okay, Golgi vesicles. If to an unexpert eye and to most people here in Tillman, you would ask them to differentiate between the Golgi and ER, I'm not sure we'll be able to do it. Okay, so this is the endoplasmic reticulum, and it's very obvious that this is indeed the ER because it's scattered with these black dots here, which are the ribosomes, and that's make it the rough ER, right? Okay. I'm not sure what they're trying to. So, so you see these, there are kind of black dots right here that you would not find. Well, the resolution is not too good. In a better resolution, you'll know that there is the same structure scattered with dots and not scattered. Maybe here it's less obvious. I'm not sure what we are trying to point at here. Okay, the plasma membrane, obviously, which surrounds the whole cell. This is something, the cell exterior, right? So it's the extracellular matrix or intercellular space, same thing. Okay, let's look at another figure. What is this? First, do you have any idea if we are inside the cell or outside the cell? Inside. I would agree, because, and why? Why is that?
Because of the bones of the ER.
Right, so you see these bones here, this is the ER, it's a more, now you see the ER and the black dots, which are the ribosomes, so this is the rough ER, and we don't see, and we are still having passed the plasma membrane, so we're still inside, correct? So what are these? I think, yeah, I would say these are Golgi. Glycogen. So inside the cell you sometimes find glycogen storage for high availability of the more energetically available saccharide glucose. Mitochondria. So this is a section in the mitochondria that you see just you slide some of the matrix inside, some of the foldings inside the matrix, and you will left just with a few sliced foldings. This is the smooth dial, okay, not the Golgi, the smooth dial, and this is the rough dial. So here it's very obvious that on one you'll find the ribosomes, and on the other there are no ribosomes at all. Okay, this is nucleus, and inside the nucleus, nucleolus, usually denoted with a small n. Okay, heterochromatin and eochromatin, we haven't mentioned these two forms of chromatin. These are just open chromatin and closed chromatin. But it's the chromatin inside there. Okay. What is the big zoom in right here? Mitochondria, and now you see very beautifully the foldings in the mitochondria. And you can separate from the inner membrane and the outer membrane, because you see the two layers of the membrane very distinctly. Okay, these are several inner structures in the mitochondria which you haven't mentioned. Chris said these are different terms for the foldings inside the mitochondria. Intermembrane space, which we find also between the nucleus membrane, which have two layers. These are matrix granules, never mind what they are for. The matrix, okay, I'm not sure what the difference is because they are in the matrix. But this is a nice image of the mitochondria. Okay, and that's that. So that was organelles of the eukaryotic cell. And now another organelle, which is more like a group of organelles than just a single one, is the cytoskeleton. That's why it will have a section of its own. Okay, it's composed of three principal components. First one is the actin filaments, which are also sometimes called microfilaments, two different names for the exact same structure. They are the thinnest among the three components of the cytoskeleton. They are about 9 nanometers in diameter. They have a twisted two-stranded structure. And the building blocks from which they are composed are the protein actin. So this is the name of the protein. And each sphere, like here, represents the protein, and this is the complex structure that we get, the actin filament. Okay, and the thickest one, thickest, almost thick, thickest, I can say thick. Thickest one are microtubules, which are hollow tubes. They are about 24 nanometers in diameter. Their walls are formed from adjacent protofilaments, so each of these is called protofilament, and the subunits, or the building blocks, are two different kinds, or two different isoforms of a protein, the alpha tubulin and the beta tubulin. These two similar but distinct proteins compose the microtubules. And the intermediate filaments, which have an intermediate width of about 10 nanometers in diameter, actually the single protein is a diverse family of proteins that we call them together in intermediate filaments. And the cytoskeleton is formed from these three components, which interact between them and interact with other proteins. And we can mention for each one, for each component, the principal role that it performs in the cell. So microfilaments, the thinnest ones, are, together with other membrane-binding proteins, form a skeleton or a mesh underlying the plasma membrane. So they are the principal determinants that determine the way the cell, the morphology of the cell from the outside. They form the mesh that underlies the plasma membrane. And so cilia and other structures that protrude from the cell surface usually is formed or stabilized by the microfilament. The intermediate filament, the diverse family of proteins, supports the nuclear membrane inside the cell, inside the cytosol, and from the outside they help connect cells into tissues. So they have principal role in cell adhesion. And macrotubules radiate from a protein complex that is called centromeres, which stands for, and together they are called the microtubule organizing center, MTOC. And upon them, several subcellular structures and organelles are arranged. And another thing to say about microtubules, and it's a result of the fact that they are built of two different proteins, the alpha and beta tubulin, is that they have ends with distinct properties. And this is just to state, okay, so microtubules are sometimes referred to as the highways of the cell, and in these highways you have directionality because of the different properties in each end. And so an organelle that's transported on this cellular highway would move unidirectionally, and you would avoid collisions between two organelles moving on opposite sides, two opposite directions. And this is just the image that shows the microtubules when they radiate from centromeres, here in the middle in yellow. So it's a system of highways, so to speak. All right. So this was the cytoskeleton, and as we ended the protein structure and function chapter by mentioning a few methods in the lab we have to purify and isolate proteins, we'll do the same here. So purification of cells and their parts. Okay, if you want to isolate or at least enrich a fraction with a lot of with a specific kind of cells, so a beautiful machine that performs exactly that is called the fluorescent activated cell sorter, or the SPAX. And what it does, it separates cells that are labeled differently with a fluorescent reagent. So the preliminary step would be to mark from a mixture of cells a subgroup of cells that have a specific protein, that present a specific protein on their surface. You would then be able to mark this subgroup of cells with a fluorescent dye or reagent. Okay, next what you have to do is to take this cell mixture or cell suspension and start flow it inside a tube in the machine, cells are forced to pass one by one, and then they meet a system of detectors that have a laser beam, scattered light, and fluorescent light detectors. And each cell separately is determined how much fluorescent does it have, or is it not labeled at all with the fluorescent line, which dictates whether it belongs to a certain subpopulation or not. And proportional to the amount of fluorescence that the cell right here has, the machine loads it with negative charge. Okay, so the more fluorescent the cell is, the more negative charge the cell would have, and then the cells are passed through an electric field, and the more the negative cells, the more the negative a cell will be, the more it will migrate towards the cathode, and you will then be able to connect it in a separate test tube. And from here on, you can grow these subgroup of cells on a petri dish. You can do specific molecular assays on them, and so on and so forth. But what this machine gives you is exactly in this, which is exactly in this step, is that you collect different cells in different test tubes, or at least enrich for a specific cell type very, very effectively. This is just to show how effective the machine enrich for a specific cell type. So the red and blue populations were separated to two different test tubes. Okay, so this is back. And then point here is to separate one cell type from another based on a specific feature. Next, if you want to separate organelles from inside the cell, so what we first have to do is we have to go through the plasma membrane, right? And we can do this either by, so we have to rupture the plasma membrane. We can do it either by an ultra-frequency sound delivery, which is called sonication, hypertonic solution, or solution low with salts, or just use a good old high-speed blender, not very sophisticated, but still you just have to break the plasma membrane and it works. Okay, and then what we get is a homogenate that includes even pieces of tissue and different cells and different organelles. And then if you filter this homogenate, you can take only the soluble part of it, which includes the cells and the organelles that were not the cells anymore, sorry, but the organelles. Okay, and now you have different protocols of centrifugation and to enrich or isolate a specific organelle. We know that if we centrifuge for 10 minutes in 600 G, for instance, the sediment would be formed mainly 90% from nuclei. And you can then collect only the sediment from this test tube. And if you continue and centrifuge 5 minutes in 15,000 G, the mitochondria, chloroplasts, and other organelles would be sedimented right there, and so on and so forth. So these protocols were optimized for several years, and we can just use them for different cell types. And altogether, it's called differential centrifugation. And now, as was the case for proteins, a more subtle separation of organelles would be by using a test tube that has glucose. Is it the glucose or the sucrose here? Sucrose. Okay, so it's sucrose gradient. So this test tube, before you load it with your sample, has a more and more dense sucrose in it. Each band, each layer has increasingly dense sucrose. And if you centrifuge, then you load your organelle fraction right here, and you centrifuge it for this and that time. And then each organelle, based on its size and shape, would be found in different layers. So mitochondria would be right here, and you can collect only this band very easily after centrifugation. Okay, and lastly, the purity of the organelles after you've enriched for a specific organelle or simply isolated them can be assessed either by electron microscope. Just again, prepare electron microscope figures from your samples and look for organelles that shouldn't be there. Or, if possible, if you have organelle-specific markers for your organelle of interest, then just mark for it and see if you have the markers that belongs to your organelle and do not have the markers that do not belong to your, that belong to other organelles than what you were trying to purify. Right. And the last method we mentioned, a rather elegant one, is based on linking some organelle to a much heavier anchor, sort of, which is actually a bacterial cell, and then centrifuge them with a much slower centrifugation, which allows much better enrichment for the organelles than a harsh centrifugation. So, for instance, here it's described for vesicles, neurotransmitter vesicles, that are most of the time covered with a protein named clathrin. Then if you have an antibody, remember these are proteins that recognize other proteins, an antibody that recognizes clathrin and sits covalently linked to the bacterial cell right here, and then you just flow a mixture of different organelles to this environment, so only the clathrin-coded vesicle would link via the antibody to the bacterial cell. You can then, after several washes, be left only with these clathrin-coated vesicles, and you can centrifuge them very easily because they are linked to a very heavy anchor. Here's an electron microscopy figure. It's one of the times in biology that things really look like the system. Sorry, yeah, impressive. Okay, so this is, here this schematic representation is only for the vesicle, but it can do the same thing if you have the proper antibody to mitochondria and to nucleus and other organelles. Right? Okay, so we went through the basic characteristics and structure of the lipid components of the biomembrane. So, in a bird's view, the different organelles that we find in eukaryotic cells, they are the cells with nucleus. Separately looked at the cytoskeleton, and then mentioned a couple of methods we have in the lab to purify different organelles. Let's take a break now, and then continue with the next chapter. 15 minutes. קלטרים זה משושים, קלטרים זה אקסגון. יש משושים, אני חושב שיש גם כאלו של מחופשים, פה זה משושים. פה זה 5. קלטרים זה בדרך כלל אקסגון. פה זה 5, נכון. אז זה 3, 4, 6. אקסגון ופוליגון. באמת? שזה איזוגי? לא יודע.
לא 5.
לא, אבל יש הרבה סיפורים שהם פנטואלים.
50.
אז לא יודע, מה, אתה אומר באמת?
לא, אז אולי לא,
חלבונים יוצאו את זה?
אבל כאילו, זה פרסום.
וואלה.
שמצאו את הסימטריה של 5 בטבע.
אבל אז למה?
אבל לא במולקולת אורגנית, בכבישים.
בכבישים, כן.
מה זה קלטרים? זה מולקולת?
כן, זה חלבון אנדוגני, זה נמצא בתאים. הוא זה שבסיקולה עוברת מהממברנה ונכנסת לתוך התא, האינטרנליזציה, אז הוא אחראי מאוד לזה, כי הוא שולט אותה פנימה כזה. האינטראקציה בין הרבה מרכיבים של הקלטרין יוצרת את הקוט הזה, ובעצם תוך כדי שהוא נוצר הוא מושך תפיסה של הממברנה פנימה, זה המודלים שלו. אני בדיוק הייתי מתחילה.
שאלה, אנחנו נלמד קצת על מטילציה של DNA,
האמת היא שלא. התשובה היא פשוט לא. יש איזשהו סיכוי שלקראת הסוף, אולי זה איכשהו ייכנס בקצת, אבל התשובה היא שלא. אין ספק שזה הנושא. first of all, I'll send you by email after the class um, the question page for the last chapter we just finished, the biomembranes, and also an article that you should read for next time, a Candel paper from Science. Yep. So and then we will read it together in class in the first hour of next time. Okay. So we will start right now the transport of ions and small molecules across cell membranes chapter, mainly based on the 7th chapter in the textbook. Okay, so if the previous chapter was about biomembranes, and now we start seeing some of the processes that happen on or across the biomembranes. It has to do a lot with also with neurobiology, transport of different molecules, among them ions. Okay, it's a big chapter, so we will start with an overview of membrane transport, just as a warm up, and then we will focus on ATP powered pumps and the intracellular, and see that they are the molecules that determine the intracellular ionic environment. Then we will focus on non-gated ion channels that transport ions that have no gate component in them, and we will see that they are the ones that determine the resting membrane potential. Next, co-transport and by symporters and antiporters. Some transport proteins can transport more than a single molecule per cycle. So these are symporters and antiporters. We will meet them. Then, very briefly, just mention the channel that's unique for water, what is called the aquaporine. Then focus on voltage-gated, in opposed to non-gated ion channels. There are gated ion channels that are gated with a gate component that's affected by different features, stretch, mechanical pressure, electrical, or just a volt, electrical potential, and so on. So these are the voltage-gated ion channels, and these are the main components that generate the action potential, or allow for the active propagation of action potential along nerve cells. And we will finish with a chapter that describes the major components we find at the synapse site: neurotransmitters, receptors, transport proteins, all these components that are involved in signal transmission. Okay, so let's start with the overview. Okay, so this is the plasma membrane. There are just a few molecules that can cross this membrane in a passive manner without any transporter. These are the small gases, which are permeable to the membrane. Small uncharged polar molecules such as ethanol and water have a partial permeability. So although it has partial permeability, it has its own transporter, what we call the aquaporine, which we will meet later on. But still, it has some capacity to pass the membrane in a passive manner. But for all of these molecules, the large uncharged polar molecules, ions, which are obviously charged, and other polar charged and polar molecules such as amino acids, ATP, lots of essential molecules for the cell, have zero permeability to the plasma membrane, and they have to have some transporter to actively be transported into the cell. And these are the membrane proteins that mediate the transport of these molecules. Okay, all transport proteins are, well, it has to be this way, are transmembranal proteins. Again, you remember the three types that a protein can interact with the membrane. It can be anchored on the membrane. It can be just a peripheral protein that non-covalently interact with the membrane, or just does not interact with the membrane at all. Or it can just be in the membrane, sits there, and in this case it would be called transmembranal proteins. And transporters have to be transmembranal because they have to form a hydrophilic channel channel inside the hydrophobic surroundings that is the membrane. And in lots of them we will find structure that we've mentioned, multiple membrane spanning alpha helices. So for transmembrane proteins, we've mentioned this, we call it a motif perhaps, of several alpha helices parallel to one another, a very stable structure that can sit stably in the plasma membrane. Okay, so as I said, the transport proteins form a hydrophilic surrounding for the hydrophilic substances to pass through. And it's a series of conformational changes that are in the base of the mechanism of action of these proteins. We'll see specifically for each kind of transporter. And this is just a general view of the three principal transporters that exist. ATP-powered pumps, ion channels, and, well, they are simply called transporters, as the whole family is called, but these are transporters that are either uniporters, symporters, or antiporters. Okay, we'll see each one of these in the chapter later on today, but for now, just appreciate the rate in which each transporter transports ions or other molecules. So the ATP power pumps are the slowest. They can transport something between just a single to 1,000 ions per second, compared to ion channels who can pass much more than in a much more rapid way than they can. So they can pass 10 to the power of 7 or 8 ions per second. And the huge difference between these two is mainly because, well, each transition of an ion or a molecule here equals just transition of a single molecule. Sorry, let me try again. So each cycle of action of this protein, each transport round or cycle equals the transport of just a single or just a few molecules. In opposed to this case in which a gate is opened, and then lots of ions can pass through it. So here, in opposed to here, each opening equals transition of lots of ions, and that's why the rate is so much higher. And somewhere in the middle we find transporters that can deliver something between 100 and 10 to the power of 4 molecules per second. Okay, so these two have to do, the mechanism of action has to do with a more complex conformational change, and hence they are slower than the ion channel. You can look at it this way. Okay, so let's start now with ATP-powered pumps, where we'll see that they determine the intercellular ionic environment. So these proteins are ATPases, which means they can hydrolyze ATP, the adenosine 3-phosphate, and that's what gives them the energy to move an ion against its gradient. So each time we will look at these rectangles always describes the direction of the gradient. So this is downhill and uphill of the gradient of the red molecule, for the red molecule. So ATP-powered pumps would use the energy stored in hydrolysis of ATP to ADP and non-phosphate to move this ion against, or uphill against its concentration gradient. And when we say a gradient, well, it can be either the gradient can be either chemical concentration gradient or electric potential, or many times it will be both. Right. So chemical concentration, I assume we all know what it means. So electric potential means that just if an ion had a positive charge, going into a negative surrounding will be difficult to it. In a very simplified way. Alright. All ATP-powered pumps are transmembrane proteins, obviously, and they will have, let's wait with the table, and they will have one or more binding sites for ATP in their cytosolic sites. So the ATP molecules are there in the cytosol, and they bind to the proteins from the cytosolic side. And they are the components in the cell that generate and continuously maintain throughout the cell life the ion gradients across the cellular membrane. So ions do not have an equal concentration in both sides of the plasma membrane for any kind of cell, not only neurons. So each cell generates and maintains a specific ionic environment, and this table describes the basic, the gradients, the chemical gradients of the basic physiological ions. So you don't have to remember these numbers by heart, but just you do have to remember that for the most important ions for us, potassium, sodium, chloride, and calcium, you have to remember what's the directionality of the gradient. And it's quite easy because potassium has high concentration inside the cell and low concentration in the blood or outside the cell. And it's opposite to sodium, chloride, and calcium, which have a gradient inwards. The chemical gradient is inwards towards the inside of the cell, because they have high levels outside. Okay, so if you open a specific channel, you have to remember which side, which direction would each ion have to go. And this table, these parameters here, are again generated and maintained by the function or the action of ATP-powered pumps. And just to appreciate how essential this process is for cells, so it's worthwhile to look at this fact that up to 25% of ATP produced by nerve and kidney cells, which have a lot of stuff going on in the plasma membrane as well, is used for ion transport. Or the ATP is used for ion transport by ATP-powered pumps. So this is a quarter of the available ATP in the cell. Just think of how many additional processes a cell has to have or is involved in besides ion transport, but still a quarter of the ATP, of the available energy for the cell, goes for maintenance of these ionic gradients. Okay, there are four principal types in nature, generally, four principal types of ATP-powered pumps, and we will only mention here the P and V classes of ATP-powered pumps, and just brought the last to a full picture. So let's start with the first one, the P class pump. It's a highly conserved pump. It's found in many kingdoms in nature, and it always sits on the plasma membrane and transports ions. And now all P class ATP-powered pumps have the same mechanism of action or operational mechanism. So let's just look at one specific case, and from there generalize to all the other family, all the rest of the family. So this example is for the muscle calcium ATPase pump, which pumps calcium ions from the cytosol into the sarcoplasmic reticulum. So, sorry, they do not sit in the plasma membrane. This one sits on the sarcoplasmic reticulum. It's a specific kind of endoplasmic reticulum that we find in muscle cells, and it's a huge storage for calcium. But usually P-class ATP pumps would sit in the plasma membrane, and also in some internal organelles such as the sarcoplasmic reticulum. Again, a relative of the endoplasmic reticulum in muscle cells. Okay, and the fact that the SR, let's call it SR, the SR is densely packed calcium ion is thanks to the action of this ATP pump. Okay, so the calcium ATPase has a domain right here that sits in the cytosol with an ATP binding site, and with an amino acid which is always an aspartate. It will be more clear in the next slide, but it's always the same amino acid, aspartate, which is going to be phosphorylated right here, aspartate. And it has a transmembranal domain where it has two binding sites for calcium. Here they are empty, and these sites are also empty, but these are the binding sites. The calcium gradient from the sarcoplasmic reticulum to the cytosol is in this direction because we've said that the SR is fully packed with calcium. Okay, so everything starts when calcium from the cytosolic side binds to the binding site in the transmembranal domain. ATP binds to its binding site in the cytosolic domain, the cytosolic binding site. Then when this happens, when calcium and ATP binding sites are, or they populate their sites, phosphorylation of aspartate occurs. This happens right here. The ATP becomes ADP, and the extraphosphate sits right here on the aspartate amino acid, which is now phosphorylated. And we've now gone up the energy level for this protein, which is the fuel for the conformational change from E1, which was up till now, to E2. And the conformational change drives, so if in E1 the calcium binding sites face the cytosol, now it's the other way around, and these binding sites face towards the SR. In this conformational change, the affinity, the strength in which these calciums binds to their binding site, decreases rapidly, and they are released from the binding sites into the SR. SR gains an additional 2 calciums. Then dephosphorylation of aspartate residue right here, the long phosphate leaves its binding site, drives the conformational change from E2 back to E1, where again the calcium binding sites face the cytosolic side. And the protein is ready to transport the next 2 calcium ions. This was a schematic description of operational mechanism of the calcium 2 ATPase. And it's quite similar for other ATP pumps. Okay, so the net reaction here is taking 2 calcium from here and move them against the concentration gradient into the SR. Okay, let's look at a water accessible model of the same protein. So these are the transmembranal domain. This side is the SR, cytosol. Never mind this domain. So this phosphorylation domain, that's where we'll find always the aspartate. So they all have a conserved aspartate residue at the same, relatively at the same spot, at the same domain, right here in yellow. The orange domain here is the one that has the nucleotide binding domain. And in the more simplified cylinder model, you can see 2 important things here. So first, this is E1, and this is E2. It's not that obvious in the model, but still, if you look hard, you'll note that, okay, so in E1, the 2 binding sites for calcium are more exposed towards the cytosol than here, and here, the same sites are more exposed towards the SR. So this is sort of the gate that either is open towards the cytosol or towards the ER, somewhere between these 2 cylinders. And the second thing to note is that the orange domain, the one that has the ATP site in it, there's a major translocation of it from one side to another. So you see it compared to the yellow domain, it moves right beneath it, and it drives the conformational change up here. That's what the model states. Okay? Right, so that was the calcium ATP powered pump. Okay, another example would be for the sodium-potassium ATP pump. So that's a nice one. It moves not a single ion but 2 in each cycle of action. Okay, so this time the channel has, the pump has an ATP binding site right here in the cytosol. This time it sits in the plasma membrane. So this side is the exterior of the cell. ATP sites right here. Sodium, 3 sites for sodium right here in the transmembranal part, and also 2 sites for potassium. You see here that it's into potassium, again in the transmembranal site. These are, as you should know by now, are the gradients for sodium and potassium across the plasma membrane. Sodium would like to slide into the cell and potassium the other way around. Okay, now if an ATP from the cytosolic side will populate its binding site, and the same for 3 sodiums from inside the cell, we start with the E1 state. we will have phosphorylation of aspartate right here. The same thing occurs. It's still a P-class pump, so we will always find that always the amino acid that will be phosphorylated is aspartate. And then, which drives the conformational change to E2, where the binding sites for sodium and potassium for this matter now face towards the extracellular side. Okay. In this state, the affinity for the sodiums diminish substantially, and the sodiums leave their site, and the potassium populate their binding site. So we are still in E2, and now the phosphorylation of the release of the non-phosphate from the aspartate again drives us back to E1, as was the case previously, and now again we're facing towards the cytosol, and the two potassium ions lead towards into the cytosol, because in this case their affinity to their sites diminish. And that's it, and we're back in with two empty binding sites for the two ions in an E1 case. So the net reaction here is taking 3 sodiums from the inside, put them out, and taking in 2 potassium ions. Right? So this is actually what generates and maintains the high sodium outside, high potassium inside chemical gradient. Okay. Okay, so this was a bit about the P class pump. About the V class, which is only a proton pump, we won't see the operational mechanism. We'll just say a few words, see where it sits. Okay, so all V class ATPases transport only protons, only hydrogens, and they are always localized to the membrane of lysosomes, and they sit there and acidify the lumen of the lysosomes. So that's the lysosome, the V-class ATP pump, and it hydrolyzes ATP in order to move a hydrogen into the lysosome. More hydrogens here mean lower pH, meaning more acidic environment, and that's good for degradation process that occurs right there inside. Okay, this is what we call an electrogenic process. So the V-class ATPase performs an electrogenic process in which the net charge in this process is not neutral, it's different from zero. Because if you move into the lysosome more and more positive charges, then very rapidly there will be a high enough positive charge inside to move any further positive charges inside. And in order to accumulate enough hydrogens to move the environment truly to an acidic environment inside the lysosome, you have to either move in an oppositely charged molecule, such as chloride, or move out similarly a positive charge in order to gain relatively neutral charge, gain and loss in the lysosomes, but still accumulate more and more hydrogens inside. Because otherwise after transport of just a few hydrogens, you will not be able to transport any further hydrogens, simply because of the inside positive charge. Okay, so, and in this case, it solves the problem usually in lysosome with the chloride passive channel. It's enough to open this channel for chloride, and it will flow in simply because of the positively charged lumen of the lysosome, and to allow sufficient accumulation of hydrogens inside the cytosol, inside the lysosome. Okay. So we saw that the ATP powered pumps generate and maintain intracellular ionic environment. And now for non-gated ion channels. And the way they, together with the ATP powered pumps, determine the resting membrane potential. Okay, non-gated ion channels. So channel proteins transport either water, so this will have a specific section, or other specific kinds of ions and molecules, only down their concentration gradient, either concentration or electric potential gradient. So again, this is the gradient for the red molecule, and a channel that's open is, if it doesn't matter if it's a passive channel or an active channel. A channel, when we say the fluorine is a channel, its action can have tremendous consequences on the cell. This is what generates action potentials in nerve cells. But still, when it's open, the only movement you'll find is a movement of an ion down its concentration gradient. It cannot go the other way around. Okay, so now we are discussing non-gated passive channels, and here we're looking at a channel with a gate. I just didn't have a graph for a channel without a gate, but passive channels, non-gated channels, what we call, just channels that do not have any gate component. So as long as they are there in the plasma membrane, they transport ions. If the cell wants to stop this transport, it has to remove the channel from the membrane. In this way, the transport would be stopped. But as long as the channel, the non-gated passive channel we're discussing right now, is there, then ions can pass through it. Okay? Okay, it'll be more clear when we'll meet the gated channels and then see the difference. Okay. So each of these physiological ions have their own specific selective channels, and each one passes through it down its concentration gradient. Pumps and ions together are responsible for the electric potential across the plasma membrane, which is not only for neurons, but for lots of oils. For neurons, it's most usually around minus 70 millivolts. For all cells in nature, it's always negative, and quite close to minus 70 millivolts most of the time. And electric potential generation by ion channel selectivity, in order to understand how do we achieve this negative potential across the cellular membrane, let's consider the following system. Okay, so we're looking at a tank with two separated compartments, and in between them an impermeable barrier. And we have just one instrument of measurement. We have a potentiometer right here that measures the potential between the two compartments. And let's also assume that we have high concentration of sodium, in the right side compartment, which is equivalent to the extracellular medium, to the outside of the cell, and low levels inside the cell, or in the left compartment. And the other way around for the potassium, which has high concentration inside the cell and low concentrations outside the cell. The fact that you have the chloride here and here, it's a salt. This is the way we add it to the system, but you can ignore for the sake of the experiment the chloride right here. Because it's the same. Chloride is equal. Okay, so for now the system, or the measurement, the potentiometer would show zero potential. 0 millivolts. Now it's enough to open a passive channel. Nothing, it doesn't have to do with ATP hydrolysis or any kind of energy. The energy that's stored here and going to be implicated is the chemical gradient energy. So it's enough to open a passive but a selective channel for sodium, for instance, and then what would happen? The sodium would start to flow down its concentration gradient, would accumulate a positive charge in the left compartment, would accumulate negative charge in the right compartment, would be accumulated. The potential, and then you have potential already, and the potentiometer will show negative something, minus 60 millivolts. Never mind. And this is how. Okay, so these concentration gradients are formed, generated, and maintained by the ATP powered pumps we've discussed. And the passive holes right here are the non-gated channels. And so you see that the first step is achieved by the pumps. The second step of the generation of the potential is achieved with the passive channels, and together you get a potential, an electrical potential across the plasma membrane. This is why we sit at around minus 70 millivolts across the neuronal plasma membrane. Okay? Okay, what would happen if there would be no ATP powered pumps? And still you would have passive holes right here. Okay, never mind. if you have no ATP vibrance, you wouldn't have the chemical concentration gradients right here, and even if you open a passive holes, there will be no flow because there will be no chemical gradient. What would happen if the same amount of passive holes for sodium would be open also for potassium, with the same rate of transport, with the same characteristics? So potassium would also flow from here to there, and the net charge would be zero. And again, you would have no electric potential. So you have to have differential transport between the similar, identical, between ions with the same sign. Okay. Or I could say that, in other words, if this channel would not be selective for sodium and would transport potassium and sodium in the same rate, the same manner, so again, the same thing would happen. Yes?
What makes it specific for sodium?
Right, so there are several chemical characteristics in the protein that makes it specific. We will see one example for the potassium channel, in which we think it's a solved question, to solve the research question, if we know why it's selective for potassium. For sodium compared to potassium, it's quite... Okay, let's see about the potassium in a couple of slides. Okay, I show you how we're getting there right now. The plasma membrane of animal cells contain just a few passive channels for these ions, but mainly and a lot of passive channels for potassium. And because potassiums have high concentrations inside the cell, and you put a lot of passive channels in the plasma membrane, they leave the cell, leave a delta charge inside the cell, so you get a negative charge for all cells. It's simply because mostly the passive channels that sit in the plasma membrane are for potassium, and not for the other ions. And this is also the reason why we usually sit quite close to the battery, what is called the reversible potential for potassium. And I won't define what it is, so you can look at it. The battery or reversible potential for ions, just look it up after this. Okay, the outward flow of potassium ions through this channel that we said is the one that determines the inside negative membrane potential. Okay, we already said what we mean by non-gated. Now we're looking at the potassium selective ion channel, passive ion channel. A channel without a gate. It's a tetramer. It's composed of four. It's a homotetramer. It's composed of 4 identical subunits. Each subunit is, you see here, a single subunit, and each one is formed by composed of 2 alpha helices. That again, it's a structure that sits nicely in the plasma membrane, and then a loop between them. And in the loop, or the segment that links them, is called the P segment, and somewhere in the P segment you have a loop. And in the loop, this is the region we call the selectivity filter, and what it actually has right here is a series of amino acids that project their carbonyl oxygens, the carbonyl oxygens that belong to the backbone of the protein, towards the channel that's formed between the four subunits when they are linked. And this is what causes the selectivity for potassium, more specifically in the next slide. We'll see how it goes. But still more generally, so this is an up view of the channel, this is a side view, this is the plasma membrane. These are just 2 subunits, and you have 2 more outside of the board and into the board. So the channel is formed between, or in the interface between the 4 subunits, right here. This cavity right here is usually called a vestibule. You find this vestibule or cavity in many ion channels. Okay, the exterior, the cytosol. Okay, and now we will focus on this region right here, the selectivity filter. So indeed it was a long-lasting question. How does a channel that transports potassium, which is bigger than sodium, would not allow a passing through the same channel of sodium, which is a smaller sphere? So it's quite intuitive to think, to understand why a small channel would not pass a bigger sphere, because the bigger sphere would just not pass through a channel with a smaller diameter than the sphere. But here it's the opposite case, in which a bigger channel does not allow the passing processing of sodium. Okay, so again, there are amino acids right here that project carbonyl oxygens, and these are exactly the carbonyl oxygens of the 4 subunits. Each oxygen here belongs to each carbonyl of an amino acid from each subunit of the tetramer. And when the potassium passes through the channel, that's the way it looks like. It interacts with the 4 oxygens. A step back. Before the potassium passes through the channel, when it's in a soluble state, so you remember that when you put an ion inside water, it is being roped with water molecules due to electrostatic interactions. So because the potassium is positive, the oxygen faces it. And so this is how it looks when it's outside the channel. And what the channel really does, as you can see right here, is really mimic the structure of the potassium when it's in a hydrated form. And so the activation energy, the energy of moving from here to there, is quite low. And this process, passing the entry of the potassium to the channel, happens very efficiently. All this in opposed to the sodium. So again, sodium outside the channel looks like this. It's roped with a shell of water molecules. But when it tries to pass through the channel, simply the distances between the oxygen, which mimics the structure of the potassium, hydrated, do not fit with the sodium, and the activation energy to move from here to there is too high, and this process does not occur almost at all. And okay, so it's all about the activation energy of the entry of the ion to the channel. This is the reason why potassium passes through the channel and not sodium. This is the reason for the selectivity of the potassium channel to the potassium ions. Okay, just a few more notes. So these are usually glycine residues in a consensus sequence that sits right here in the selective filter region. Glycine, okay, right, in the P segment. And just note that we are looking at 4 oxygens right here, but there are an additional 4 oxygens hidden beneath these 4, because it's a cube of 8 water molecules usually that rope an ion. Depends on which, but usually. So now a side view, we will see we'll see the cube of water molecules, the upper 4 and the lower 4. They're not aligned in a linear line right here, right? You have a square here and a square there. Okay. So now again we're looking only at the red, what was red, the P segment, selectivity filter in the P segment of the potassium channel. This ion right here is exactly in the transformation state in which it still interacts with 4 water molecules from the cytosolic side, but from the exoplasmic side, and is engaged already with the 4 oxygens that are part of the protein. Now several potassium ions can pass through the channel, but you would have to each one to give them 8 bonds of 8 interaction with oxygen, as we saw. And so they're actually, it's not like that several ions pass through the channel, but rather like this, where we have 2 alternating states, but which potassium ions pass through the channel. So they populate either the first and third spots, or the next step will be the second and fourth spots. And then in this way, each one gets 1, 2, 3, 4, and another 4 from the outside and inside subunits of the tetramer, and all in all 8 interactions with an oxygen. And that's the way it is stabilized. Okay, this was selectivity filter of the potassium channel of potassium ions. Yeah, that's it. Okay. Let's start with co-transporters that are either symporters or antiporters. Okay, some transport molecules can transport single molecules, and some of them transport 2 molecules, and always use the energy stored in the downhill movement of one ion, downhill in its concentration gradient, coupled to the movement of another ion up its concentration gradient. Transporters that move two ions to the same side of the plasma membrane are called symporters. Sim meaning similar or to the same side. And transporters that move two ions to opposite sides of the plasma membrane are called antiporters. But in both of these cases, each time one ion is transported down its concentration gradient, the red in this case, while the other one is transported against its concentration gradient. So this energy is coupled to this process. It's used to move this process, and again the same thing happens here, only the concentration gradients for in this time are in similar directions. Okay, so if the ATP power pumps use chemical energy, here we see energy that's stored in the chemical gradient of ions to drive the process. Okay, this is what we've already stated. Simple transport molecules and contransported ions, the one that moves uphill and the one that moves downhill into the same direction, and antiporters do it for opposite directions. Let's just see an example of a few of these proteins. So in the cells we find sodium, potassium, sodium, hydrogen antiporter, chloride bicarbonate antiporter, HCO3, 2 sodium, 1 glucose symporter, so delivery of glucose into the cells is also based on the transporter. And let's see I think an elegant example of several co-transporters that are involved in regulating cytosolic pH, how acidic would the cytosol be. So we are looking at the percent maximal rate of ion transport, or just how effective the protein is, or how functional it is. In a neutral pH, somewhere around 7, so these two proteins, this transporter and this transporter, almost do not function at all. If we move to an environment rich with the hydrogen, to an acidic environment, so this transporter comes into play, and it's a sodium hydrogen antiporter. As you see, it moves the two ions to opposite sides. It uses the downhill movement of sodium, which is it's a process it's an exotonic process, right? Because sodium is high outside, and also the inside of the cell is negative, so it has all good reasons to go into the cell. So it uses this very high energy that's stored in the sodium chemical gradient to move the hydrogen outside of the cell, to push it towards a more basic environment. If we go to too basic, too much to the right, so this chloride bicarbonate antiporter comes into play, and this one uses the chloride downhill to move a bicarbonate, which is a basic molecule outside of the cell, and again pushes us towards a less basic environment. And the overall function of these three stabilize the pH inside the cell properly. Okay, we will end today with the aquaporins, and then next time continue with the voltage gating and the different components we find in synapses. So the aquaporin, just a single slide, because it would be wrong not to mention it at all. Okay, it's a tetramer, again a homotetramer, built of 4 identical subunits. In each subunit, you find 3 pairs of homologous alpha helices, A tag, B tag, C tag, in an anti-parallel orientation in relation to one another. So the A goes from here to there, the C to the N terminal, and the A tag goes the other way around. And this structure forms a cylinder, sort of, that forms the channel in each subunit that we see right here, again, we find several alpha helices that stabilize, that is a stable structure that sits in the plasma membrane. Now, in opposed to the potassium channel, where the channel itself was formed in the interface between the four subunits, the aquaporine is different. Here, each subunit delivers a water molecule. Each subunit is a channel by itself. Still, for the channel to be open, for the protein to be functional, these four subunits have to be linked to one another. It's a conformational thing, but still each subunit in the aquaporine is a channel by itself and can deliver water molecules. Then water molecules are, when they pass through the channel, they interact with carbonyl oxygens that are part of the backbone of the channel. Again, a common theme in proteins. Right, and that's it. So, all in all, today we saw that why should cells transport ions and other molecules? So it's good for nutrition. We think it's also for probing of the cell environment. We know it's important for cellular signaling between cells, receiving cells, and also for volume, for regulating the volume of the cell, which is the main purpose or the main effect of the aquaporine. And again, it's a passive channel, right? So if the cell wants more water to pass through its membrane, it has to synthesize more aquaporine to transport them to the membrane. To transport it to the membrane, and if it wants water to stop from being transported, it has to remove these proteins from the plasma membrane. Now, another common thing, just one last thing I'll mention, is that again, these loops here bend into the cavity, into the channel that's formed between the alpha helices, and these loops that kind of hides part of the holes form the selective filter for water molecules in the aquaporine. And it's a similar thing we saw in the potassium channel, that these are the loops, fragments in the protein that bend into the channel and cover part of it or build the selectivity filter in the entry of the channel, right? So it rings the bell. It looks similar to the potassium channel in this sense. Right. Okay, so that's it for today. We'll continue next time with these two sections. I'll send you the email, the article for next time.
תודה רבה.
Yes, sure. So, upon request. So just send an email whenever you want.
Maybe we can arrange one now. What time will it be?
I can do it right now.
I'd like to just go over some stuff.
Right. So I can also let something like 20 minutes. Site is in Monad lab. You know where it is?
Okay. No, where is it?
So it's one floor below. It's third floor, first wing. So this is where Eltic is at the third wing. Right. You have to go towards the entrance and then when you go down the hall, we actually own the whole corridor. So it's like on your right, you can ask anyone.
Okay. Maybe on Sunday that would work best. Are we usually around on Sunday?
Yep. Some usually between 8 and 2, 3 p.m.
Okay.
something like that.
Oh, okay, perfect. So
All right.
Sunday morning.
Okay.
It'd
It'd be best if you send an email before, just to be sure. But
Okay,
I'm
sure.
there usually.
I'll do that. Yeah. Thank you.
אני רק אאשר לך, אני חושב שזה סבבה שהוא מתאים לעבודה כאילו, שלא תתחבר רק מתחבר.
אבל אמרת אותו סגנון עבודה כמו שאתה?
כן, זה צריך להיות ממש שהוא כאילו נוירוביולוגיה, שהוא לוקח איזשהו מרכיב מולקולרי והוא מנסה לחבר בינו לבין איזושהי תופעה נוירונלית.
פחות או יותר באותה... מה הראשון על ה-NADH?
אז הוא כמעט לא מתחבר לאיזושהי נקודה נוירונלית. הרבה אנשים, בדרך כלל אנשים לוקחים נגיד, זה מולקולה, אומרים שהיא חשובה לזיכרון. אז הנה מאמר קלאסי, כאילו, אז הזיכרון זה המרכיב הנוירונלי, המולקולה היא משהו מולקולרי, ואפשר עכשיו לראות איך כותבים ומנסים לחבר בין השניים.
ובאיזה תחום זה לנתח את המוח?
אז יש שאלות, זה עבודה קצרה, זה עמוד אחד, 600 מילה, לא יותר, באנגלית. זהו, זה כזה תשובות, כן, זה לא באמת ניתוח ארוך. ואז אפשר, אני נותן אותה בדרך כלל להגיש עד שבועיים מתחילת הספרת מבחנים.
אז מה אפשר לזה?
אני צריך ודאי אימות, אבל נראה לי שזה בערך החלום זמן. כאשר יש בערך על חודש. תתחילי את השם?
כאן אנחנו רואים שזה פתרון ואנחנו רואים שזה לעצמו בעיקרון, אבל גם בפתרון נורמלי. אז כאן אנחנו כאילו לוקחים משהו בכיוון, וגדלים אחר.
בוקר טוב.
כמובן שהבנה של הפלט זה אומרת
יש לך זהו. בעיקרון, בראי מה שהצליחו לחבר, היינו ממש חיפשים במה ששלחת. ממש חיפשים במה ששלחת. כי הייתה תחושה טיפה של... כן, ברור שאיתה אנחנו מדברים, אנחנו מדברים את הפגישה, כאילו שהקטע.